Alrighty, howdy folks. Let's pick up chapter 2, section 2. Earlier I had covered chapter 1, section 1. Let's move on to chapter 2, section 2. Mm, and this is about cash flow diagrams. And in this session, we'll just focus on single cash flow and talk about that. Single cash flows. We'll find the time value of money for single cash flows with periodic compounding. That's the interesting part. Okay, so let's see what in the world I mean by all of that. So let me try to define something. The principal P is the original amount borrowed or invested. Okay, we are looking at things in terms of borrowing some money from a bank or something like that. So if you borrow some $1,000, then the principal P is $1,000. Okay. This is also the current value or present value, right? That makes sense, right? You just borrowed the money, you have that money with you at this point of time. So that means that's the current value or the present value. And interest, I, uppercase I, is the cost of borrowing money or the reward for lending money. Uh, if you recall, I had used this word I even in the previous lecture, but that was a lowercase I. But now I'm using an uppercase I. Oh, why did I change? I did not change. So the lowercase I is actually the interest rate, but uppercase I is the total interest. That is, it's not the uppercase, how should I put it? The lowercase I is a sort of a percentage or a decimal, whereas this is the whole amount. For example, if I borrow $1,000 and after 1 year I have to pay $1,200, that means the $200 is the interest amount for that 1 year. And that is what I'm talking about as being uppercase I. Cool. It is the cost of borrowing money in the case where I go to the bank and I ask them to give me money. Then, well, it's going to cost me some money, like in this example, $200. Or if I happen to lend you the money, that's the reward for me for lending you the money, right? So I is the actual amount of interest. An interest rate is the proportion of a lowercase I in this case, is the proportion of the principal paid as interest in a single period. What is the proportion of the principal paid as interest in a single period? Okay, let's go back to that example. If I borrowed $1,000 and after 1 year, a single period is 1 year here, I paid $1,200. That means $200 is the interest. And what is the uppercase I? And the lowercase I is the proportion of the principal paid as interest. I paid an interest of 200 when I borrowed what? My principal was 1,000. So what is the proportion of interest and the principal, or the ratio of the interest to the principal? 200 over 1,000 for 1 year, right? For that single period. So I is basically 200 over 1,000 or 2 over 10 or 0.2 or 20%. That's the whole point here. Cool. Future value. Future value F is the sum of the principal and the accumulated interest in periods later. Accumulated interest in periods later. This is something that we need to talk about. And also, especially in terms of this compounding concept. Okay, anyway, I think I'll illustrate all of that stuff with an example. It's just understand right now that future value F is whatever is the total amount after n periods. Okay. All right. Compounding is the process in which interest is calculated on the principal amount plus any accumulated interest from previous periods. This is the very, very, very key and important concept in this whole thing. Compounding. What is this process of compounding? It's a process in which interest is calculated on the principal plus any accumulated interest. Okay, keep that in mind, and I will illustrate that with a nice, wonderful example in just a second. Cool. Here we go. The CFD, what? Cash flow diagram. For a single investment of P at t equals 0, compounded for n periods for a future value of f, looks as below. So we tend to do pictorial representations of cash flow because one look at it, once you get familiar with this, one look at it, you can tell, oh, you mean you borrowed some P at t equals 0, and after n periods, you got some future amount, some amount, right? And of course, sometimes, you also state as to what the interest rate is and so on. But this is, for instance, a simple cash flow. One more thing you need to notice. How come this is going down and going up, whereas this one is going up? Well, going down is a negative cash flow. If arrow is pointing down and is below this axis, time axis, then we're talking about this being a negative cash flow. And when an arrow is pointing up, it is in the positive direction here, above the time axis, then that is a positive cash flow. So think about this for a second. The example where I said I borrowed $1,000 from a bank, and 2 years later, say I pay 1,400 to the bank. Would that refer to this cash flow? I borrowed 1,000, paid 1,400 2 years later. Answer is no. Because if I borrow some money, I have money. I have that $1,000, right? If I have the money, then I have to make it into a positive. And later, when I pay 1,400, I'm losing money. I'm giving away money. So that should be a negative going down here. Oh, okay. But how does the bank look at it? The bank looks at it as, hey, we had to give this guy $1,000, so we sort of lost, at least temporarily, we lost this amount. So their cash flow would be displaying this as a negative cash flow. And later, when I pay back, as a customer, I pay them back the whole amount, then that's going to be a positive cash flow for them. So this below this, up above that, all depends on the perspective of the borrower or the lender. That's the whole point. Cool? All right. So we are going to do quite a few of these cash flow diagrams. But for a single investment, this is fairly straightforward. By the way, let me give you a heads up. Pretty soon, we're going to have all kinds of complicated things going down here, up there, and down here, and all sorts of things like that. Cool. Okay. Now, consider the following set of calculations. End of period, amount invested, interest for next period, future value at beginning of next period. These are my 4 columns. So let me start with this. End of period 0. Suppose I invest some amount P, right? What? End of period 0. Well, end of period 0 is also the same as, sort of almost same as, beginning of period 1. Try to understand that. End of period 0 is the same as beginning of period 1. The way I would like to liken it to is December 31st, 11:59 p.m. 59 seconds. Let's say year 2026. Well, is that the end of year 2026? Of course it is. But just a second later, isn't that going to become the beginning of year 2027? So, end of period 0 is almost the same as, with just with a in math we say 0 plus, slightly to the right of it, slightly to the right of it is going to be the beginning of the next period, period 1. Cool. All right. Now, if we invest amount P at the end of period 0 or beginning of period 1, and a whole year elapses, what is the amount of interest this P would have accumulated, would have incurred, accrued? Accrued is a word. Yeah. Um, P times I, right? You take the principal, multiply by the interest rate for that period, interest rate for that period, and you get the total amount. This is the I, uppercase I. Good. Now, the original amount was untouched, and that earned an interest here. So what is the future value at the beginning of the next period or the end of this period? Is you just add these two things, P plus PI. Cool. As simple as that. The amount invested at the end of this period or beginning of this period or beginning of the next period plus PI, and that gives you this one. Would you agree that's okay? I just factored out a P. As simple as that. Cool. With that, when we move on to the next one, end of period 1, then amount invested is, let me pause there and get you to tell me, what is the amount invested? Hey, come on, man. The amount invested is always P. That's what you invested. Yeah, right. I agree. However, this is the whole idea of compound interest. Okay. If we are compounding annually, after 1 year, the amount invested, so far as interest calculations are concerned, the amount invested should not be just the original amount. It should be the value at the beginning of the next period. So we have to say P times 1 plus I is the amount invested for this period. For the second period, which is the end of first period or the beginning of the second period. So the amount invested would be P times 1 plus I, which was this value. Good. How much interest would this investment have gained in just 1 year? Well, we need to take this amount invested and multiply by I. And so that's what we do. So that's the interest for this period. For period 2, where the period 1 ended and period 2 started. So this is the interest. And needless to say, what is the total at the end? Total, just add these two things, P times 1 plus I plus P times 1 plus I times I. And what? That's P times 1 plus I, the quantity square? P times the quantity 1 plus I squared? How? Simple math. Can I factor out a P times 1 plus I from both these terms? Good. If I do, would you agree I get 1 from this first term plus I from the second term? Right? P times 1 plus I times 1 plus I. Oh, but 1 plus I times 1 plus I is 1 plus I, the quantity square. That's the whole idea. Cool? All right. And moving on, period 2, end of period 2, beginning of period 3. What is the amount invested? We need to take this P times 1 plus I, the quantity square guy, and we should make that as our amount invested for this period. And needless to say, we multiply by I to fill up the next column. We add, and the same thing happens. You can factor out a P times 1 plus I, the quantity square, and you get times 1 plus I, so the whole thing becomes P times 1 plus I, the quantity cubed. P times the quantity 1 plus I cubed, I should say that. I think you're beginning to get a hang of this, right? I apologize for insulting your intelligence. So next we do this and multiply by I. When you add, you get P times 1 plus I to the 4. And now definitely you got the idea. So we'll just go and so on, we'll say. So on, and how far should we take this? Check this out. I'll say end of period n minus 1. Means beginning of period n. Cool. What would this be? Can you guess? Right? Can you guess from the pattern? I think we can, right? When we had 1, we had P times 1 plus I to the 1. When we had this 2, 1 plus I the quantity square. For 3, we had a cube. So if this is n minus 1, stands to reason, this should be raised to n minus 1. Cool, and the interest would be times I, this quantity times I. As before, we add. We can factor out P times 1 plus I to the n minus 1, and that thing will become P times 1 plus I to the n, right? Now, this is the future value at the beginning of the period. So at n, at the beginning of period n, or n plus 1, or at end of period n, this is what we have. Our intention is to stop right here. We don't want to go to n plus 1. So at the end of period n, after 10 years, what am I going to get? That's the thought process here. Cool. All right. So to find a future value given principal, interest rate, and the number of interest periods, what we are doing is we are going back to this table. So what happens if I invest P and the interest rate per period is I, after n years, so the amount I would have is P times 1 plus I to the n. So that is what we are about to say here. The table shows that the future value f sub n, on purpose I'm adding that sub n, usually we don't, um, of principal P after n interest periods at an interest rate of I is given by f sub n is the same as the future value after n years, P times 1 plus I to the n. Cool? You need to sort of memorize this formula. P times 1 plus I to the n, where the 1 plus I to the n is how should I put it? Unfortunately or fortunately, there are going to be so many terms, and you just have to know all these terms. So please don't blame me. Just try to get familiar with all these terms that people throw in, because out there in the real world, people do use those kind of terms. So you don't want to look like a deer caught in headlights when someone uses a particular term. So that's why I'm trying to introduce as many terms as possible to you. Cool? So this 1 plus I to the n in this case is called a single sum future worth factor. That kind of makes sense, right? If all you have done is you invested a single amount of money, P, and in the future, what would it be worth? That is the future worth factor, this 1 plus I to the n. Take your single investment of P, multiply this by 1 plus I, the quantity raised to n, you're going to get the future value after n years. So that is the single sum future worth factor, and is also denoted as F some blah pli I, and that, the first time I said, like, how the hell am I supposed to read that? I thought. And then, fortunately, they tell you need to read this as the F given P. F, the vertical line is given P. And this is a fairly standard notation. Uh, Probability of A given B. You will see something like probability also A given B. What is the probability that A would occur given that B has occurred? So they use the same bar like this, vertical stroke like this. So P, the F given P factor at I% for n periods. Okay. Now, the idea there being, you can say the future value F is nothing but P times this single sum future worth factor. F given P I% N. So you just multiply the present value with this factor and it's done. And the thing is, why am I saying all of this? I got the formula, man. This is pure math up here. And that makes sense to me. Why are you introducing this term? That's simply because people have tables built up. I have no idea why. I mean, this day and age, we still use tables. But anyway, so people have constructed tables for these factors. As in, they would say something like, imagine P were to be 1. And if I is 1%, for 1 year, 2 years, 3 years, 4 years, what would these factors be? So there's a table of values like that. And then they say, okay, what if it is 2%? Okay, again, for 1 year, 2 years, 3 years, 4 years, up to 10 years, whatever. So they have tables like that. And these things, this particular term, single sum future worth factor, is in fact used, and it is also written as this F given PI% comma N. So that's the reason I'm trying to introduce this concept also. In fact, I'll show you how to solve a few problems based on this factor too. Okay? All right, let's pick up a problem, make it a little more concrete instead of talking abstract. A deposit of $3,000 is made in a savings account that pays 7.5% interest compounded annually. How much money will be available to the depositor at the end of 16 years? Excuse me. Right. Take a look at the problem for a second. Pause the video if you need to. Deposit 3,000 is made and interest rate is 7.5% and it is compounded every year. And how much money will be available to the depositor at the end of 16 years. Cool. So, principal P, boys and girls, 3,000, good. Interest rate I, 7.5%, man, good, man. So that's 0.075. If you divide that 7.5 by 100, you get 0.075. Interest periods, how many interest periods? 16 years, right? And we need to find what? The future value F. All right. Method 1. Method 1 is, let's use our simple straightforward formula. F equals P times 1 plus I to the N. Plug and chug. You need to use a calculator. Go ahead and do that. And this is what you get. Cool? All right. Then, what is the second method? Well, here is where, if you look at the table, I'm not showing you the table, but such a table is available if you have the textbook, or you can go on the internet and look for single sum future worth table and you'll have one, right? The problem is, what is our interest rate here? 7.5%. Cool. You go to the table and say, hey, give me this value for this factor for 7.5%. And it goes, sorry, we don't have one. What? Yeah. However, what they do have is, when I is 7% and I is 8. They have this for different values of n, 1, 2, 3, 4, 5, 6, and so on. So even for 16, they have what that value would be. But the problem is not for 7.5% interest rate. Then what do we do, man? Okay, check this out. For the 7%, 16 years, that factor is 2.95216. Whereas for 8%, it is 3.42594. Aha. We need for 7.5%. How do we do that? Do you remember something called interpolation? Right? You know the value at one point and you know the value at another point. Now you want to know in between, for something in between, what is it? To me, this is fairly straightforward. This is called linear interpolation. And interpolation is like finding the equation of a line given 2 points. That is something in math you are quite familiar with, right? If I have 2 points, boys and girls in high school, teacher must have said, if we have 2 points, x1 by 1, x2 by 2, we can use the 2 point form, which is, and find the equation of that line as y equals y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1. This is another version of y minus y1 equals m times x minus x1. M is the slope, rise over run, and that rise over run, rise would be y2 minus y1, and the run would be x2 minus x1, as simple as that. Okay, y equals y sub 1 plus y sub 2 minus y1, y sub 1 over x sub 2 minus x sub 1 times x minus x sub 1. Alrighty. So, what? Aha. Is what is this formula got to do with what we are trying to do? I would say everything. Let's see. What do we want? We want at 7.5% what this factor is. We know for 7% the value is 2.95 blah blah. So that means take x1 as 7%. Cool. X1 as 7%. Y1 as 2.95216. And x2 as 8% and y2 as this 3.42. Okay? And what is x? X is where we want the value. That means at 7.5%. So take that to be x. So we know everything. We know y1. Y1 is 2.95216. Y2 is 3.42594. Y1 is back to this. X2, importantly, X2 is the 8%. X1 is 7%. X is 7.5%, like I said. And X1 is the 7%, right? And that way we can find out the Y. That is, we can find out F given P, 7.5%, 16. That's the whole thing I'm trying to say. As simple as that. If you need to pause and go over, please do so. The concept behind that is precisely this. And as you can see, I have done exactly what I told you. And when you do this, you get that factor to be 3.18905. And so that means if you want to find the future value, you take your principal and multiply by this factor, which we just found. Principal happens to be $3,000. And this factor we just found happens to be, for 7.5 years, happens to be this guy. And so we multiply and we get this much. Cool. What was the actual value we got when we used the formula? Let me go back. 9542.38. 9542.38. Is there a difference? Of course there is. 9542. This is 9567. So there is a $25 difference. But that is to be expected because this What we did is a linear interpolation, and that is not necessarily, that's definitely not a linear, uh, it's not changing linearly. In between are not changing linearly. So that's the idea. So that difference is okay. All right. Method three. Method three is you can use Excel. Mm, Excel, all you do is you go to a particular cell in Excel and say you will type equals, right? You must type equals. So that's when it knows. It wakes up and goes, aha, you're going to expect me to figure out the value of some function. The answer is yeah. The moment it says equals, it gets ready to do some computation. FV is for the future value, which is exactly what we want. And rate is the first input to it. What is the interest rate you're using? 0.075. And the good thing is, please pay attention. You can do 0.075 or type 7.5%. You better type the percent though. So you can say 7.5%, it understands that. Or you can just give the decimal value of 0.075. N per, meaning how many periods? 16 periods. Good. Payment, PMT, that is 0. What? What is that, man? Ah, the PMT is, we don't have that situation here, but PMT is basically if you were to be depositing the same amount every year, right? There's something called annual payment. For instance, in addition to this $3,000 at time t equal to 0, let's say every year, year 1, year 2, year 3, year 4, you keep on depositing $100. That is what this PMT would be. And so and at that time, I would have had to, I would say 100 here. Cool. And PV, what is the present value? Present value is negative 3,000. What's up with that? It has to be negative 3,000 here because I am depositing $3,000, right? So at t equal to 0, I lost, quote unquote, lost some money. It's in fact, it's a debit from my account. So that's why we have to say minus 3,000. And then Excel gives you a perfect number, positive 9542.38, which is exactly what we calculated using our thing. If you put a positive 3,000 here, it will return negative 9542.38 for you. So don't let that sign bother you too much. Just understand why it is doing what it is doing, and you are in a good shape. So this is the third method. What I think, unless stated otherwise, I'm going to stick to only method one. You, by telling you that, hey, you know what, if you want to use the tables or the Excel spreadsheet, be my guest. But I think math is good enough, and as much as possible, I'll use that. Cool. With that, let's move on to the next problem. How long does it take for an investment to triple if the interest is 8% compounded annually? In this problem, we have principal P is, oh, sorry, I should have given you some time to think about what in the world the problem is asking. Okay, how long does it take for an investment to triple? So you deposit 1,000, you should get back 3,000. If you deposit 15,000, you should get 45,000, right? The interest rate is 8% compounded annually. How many years do you need to keep this investment in so that you'll get triple your money and the 8% compounded annually rate is the idea. So, but you didn't tell me how much you invested. The truth is, you don't need to tell exactly how much. We can just use a variable for it. P should become, it should be tripled. What does it mean? P should become what? 3 times P. As simple as that. Interest rate is 8%. And interest periods n, that is something we don't know, and we'll leave that as n. And future value f is 3 times p. That's the whole idea. Cool. Method 1. F equals p times 1 plus I to the n. Plug and chug. 3p for f and the original p. Now you notice we can divide both sides by p. So that's why it doesn't matter what was the principal. As long as we are stating that whatever principal I have, it should get tripled, then you don't need to know exactly how much you have to invest at t equal to 0. Cool. So, all right, so 3p over 1 plus 1 point. Okay, we can divide both sides by p and we get 1.08 to the n equals 3. Would you agree? What? 1.08 to the n equals 3. Dang. How can we find n? Do you know how to find n? If I have 1.08 to the n equals 3? Check this out. You remember logarithms? Boys and girls, you need to take an exponential form and convert it into a logarithmic form, right? A to the x equals y implies x equals log base a of y, right? If a to the x equals y, that's the exponential form, that implies x equals log base a of y. You must know this one, okay? So, would you agree this 1.08 to the n equals 3 looks like a to the x equals y? Yeah. And x is n. So n is nothing but log base 1.08. A is 1.08, the base of 3. Cool. I don't know if your calculators are capable of figuring out with a base of 1.08. Some calculators apparently do. You can give it whatever base, but if you happen to have just a simple scientific calculator, what you can do at this stage to figure this out is you can use what is called change of base formula. So you can call this as log 3 over log 1.08. Log. What's up with this log, man? What base is this? Well, if I don't say log, the base is assumed to be 10. However, I could have said natural log of 3 over natural log of 1.08. As long as the base we are using both on the top and the bottom is the same, we are good to go. We can use base 10 like I did here, or we can use natural log base e. Just for the heck of it, go ahead and check, figure out natural log of 3 over natural log of 1.08. You should get the exact same answer, 14.276 years. Cool. Wait, what did we find? How long does it take for an investment to triple if the interest is 8% compounded annually? So if you're getting an interest of 8% per year, you need to deposit that money for 14.276 years. After that, you'll get triple the money that you have invested. Your money will triple. That's the idea. Okay. Method 2, yeah, I'll just quickly go over it. So you need to go to the stupid table again. 8%. Yeah, maybe I'll go with it. 8% interest rate. We look for number of years n for which this factor is 3. But what we see is there is nothing like exactly 3 in the table. However, we see that when n equals 14 for this 8%, that factor is 2.93719. Whereas if you jump by n equals to by 1 year, n to n equals 15, that factor becomes 3.17. Does that make sense? At n equals 14, that factor is 2.93. N equals 15, it jumps to 3.17. So somewhere in between, the factor must be 3. What is that in between n? That's what we are trying to figure out. Again, we'll do that interpolation thing. And if you do this, you get 14.27 years. I think the other way we got 14.26, if I'm not mistaken. This way you get 14.27. Cool? That's the idea. And method 3, the Excel thing also allows you to do this. You have to say equals n per n periods. Hey, find the number of periods I need to invest this. Okay, tell me what are you doing? The interest rate is 0.08, or you can say 8%. PMT, you're not investing any money every year, so that is 0. And the present value is -1. What? -1? So, like I told you, it doesn't matter what the initial investment is. I can take the initial investment to be $1, which of course in this case, because you're paying that money, you're investing the money, you should say according to Excel, -1. And then you get back what? 3 times that money numerically. So 3. Or I could have said -100, 300, -50, and 150. Any number times 3, any number, comma, 3 times that number. That's what I'm trying to say. And the future value is the 3. And type, there is something called type. Don't worry too much about that. 0. And you'll get 14.2749. Cool. What was that? Now I'm curious. 276 according to this. 2749. Okay. Cool. Ladies and gentlemen, with that, let's move on to find the present value given the future value interest and number of interest periods. Okay. Now, what if we need to reverse the process? That means we have this formula for future value as p times 1 plus I to the n. What if I want to find the present value? I know the future, and I know interest, and I know n. Simple. Divide throughout by this. Simple math will tell you the formula should be p equals f over 1 plus I to the n. Cool. This is also something that notice in lieu of what we did last lecture. Here, in this formula, we are taking the present value and projecting it forward to n periods. Would you agree with me? Taking the present value and projecting it to the future. In order to correctly do that, you need to multiply by 1 plus I, the quantity raised to n. In the last section, we talked about projecting it forward only to one period. And our formula was p times 1 plus I. Multiply by 1 plus the interest rate is what we said. Now, at that time, we said, however, if you want to take a future value and push it back to the beginning, that is, you find p given f, then divide by 1 plus I. Well, that was for one period, it was f over 1 plus I. Now we are finding that if it is n periods, you do f over 1 plus I to the n, if this is a single cash flow. As simple as that. Cool. It's a single sum present worth factor, and it is called p given f I% n, the p given f factor at I% for n periods. Cool. And so you take the future worth and multiply by this factor, and ta-da, that's how you find p. Cool. I do have a problem. If you want to receive $5,000 3 years from now, how much should you invest today at I equals 10% compounded annually? F3 is 5,000, right? F is 5,000. Interest rate I is 10%, which is 0.1. Present value P, unknown. And so, a very nice boy, good boy. Drew a cash flow diagram. Cool. So what do we need? Method 1. Apply the formula. P equals what? What'd you do, man? I thought it was f over 1 plus I to the n. Okay. 1 plus I, the quantity raised to n in the denominator, isn't that the same as 1 plus I a to the negative n on the top? That's all. That's simple math I did. Cool. So you do this and you get this. Cool. Method 2, you do this interpolation nonsense and the PV, present value of interest rate. The periods are 3 periods. Annual payment is 0. Future worth is 5,000. And so you get this number. And I think that is the same as, yeah, that's exactly what we got by our original formula that we used. All right. Good. For your 21st birthday, your grandfather offers three choices for a gift: $1,000 today, $1,500 3 years from now, or $3,000 5 years from now. If your money grows at a rate of 8% compounded annually, which alternative should you choose? Right? Pause the video if you need to, go over the three conditions and try to answer it. So, in all such problems in which we choose an alternative, we should find the value of money at the same point of time. That's the key. For instance, find the present value of all the three options, or find the future value of all the three options at one particular time. 1,500 3 years from now, 5 years, 3,000 5 years from now. So we can project everything to 5 years from now. Mm, that's going to be a little pain, but looks like a better approach in this particular problem would be to take everything to the present value, find the present value of everything. So finding the present value of choices 2 and 3 is a better strategy. 1,000 is already the present value. So let's focus on choice 2, 1,500 3 years from now. So that is the future value. Interest rate is 8%, and present value is what? So we'll use a formula, and that turns out to be 1190. So 1,500, when your grandpa gives you $1,500 3 years from now, it's exactly the same as getting 1190, as if he was giving you 1,190 today. That's the point. And if we do the same calculation with this guy, the present value turns out to be 2,041. Ooh. So what should you pick? $1,000 today, option 1, or 1190 today, option 2, or 2000 today? Oh, obviously, we'll pick this one. See? So that's how you make choices in these kind of things. Good. So that concludes this lesson. Thank you.